So we're going to finish our second set of notes for 3.2. So we're going to do examples, let's see what we have, 4 through 6. So for this first part here talks about representations of functions. So we can represent it with words. For example, an output is 3 more than the input. You can represent it with equations like y equals x plus 3. You can use an input-output table. You can use a mapping diagram which has arrows showing what outputs are coming from which inputs. You can represent as a graph. So for example, if I was to graph y equals x plus 3, this is the graph here, and this graph is also representation of the mapping diagram, which is also representation of the input-output table. So all of these are the same function here, every single one. Now, functions come in 2 different types for us, discrete and continuous domains. So a discrete domain is a set of input values that consists of only certain numbers in an interval. I like to think of this as discrete means individual points. If you have individual points showing up, that's discrete. Where continuous, the difference with continuous is from one point to the other, you have a continuous line. They're connected. So these are connected. Now, in terms of the domains, a discrete domain has individual points, where a continuous domain has inequalities as their domain and range, because it covers a span of numbers rather than individual numbers. Let's look at example 4 here. The linear function y equals 15.95x represents the cost y in dollars of x tickets for a museum. Each customer can buy a maximum of 4 tickets. So that's a key there. You need to remember maximum of 4 tickets. So first it says find the domain of the function. The domain here, we think about it, I can buy as few as 0 tickets. I can buy 1 ticket, 2 tickets, 3 tickets, or 4 tickets. I cannot buy more than 4. And notice these are individual values because I can't buy 1.5 tickets or 2.3 tickets. They're individual values, which means this is a discrete domain because the inputs cannot have partial values. I can't have a part of an input. If my input is the number of tickets, I can't have a partial ticket. I have to have a whole ticket or I can't go. Okay? Now, part B says graph the function using its domain. What I want us to do right here is to use, so we're going to use table in the graphing calculator. So I'm going to turn on my graphing calculator here. Here we go. I'm going to go to my y equals like we did in class. I'm going to type in that equation 15.95x. 15.95x. But I want to go to the table right here. And because it's in blue, I need to press the blue second key, then press table. Now notice my domain over here. I need the numbers 0, 1, 2, 3, 4. Domain is my x. So I'm going to start right here. I want 0, 1, 2, 3, and 4. These are my values. So what I do is I copy those values down on my paper. So I can make a little t-chart here with x and y. And when I have 0, 1, 2, 3, and 4, from my graphing calculator, I get the outputs of 0, 15.95, 31.90, 47.85, and then 63.80. Now I need to graph this. So I'm actually going to zoom in over here. Now I should have made the graph where it's only this first quadrant here, but we're going to scale our graph. Let's count the y values by 10, because I don't have enough to go all the way up to $63. And our x values are just going to be your normal 1, 2, 3, 4. So let's go ahead and plot these. The first one was 0, 0, which is right here. Next was 1, and then 15.95. So 15.95 is about halfway between 10 and 20, so I'm going to put a point here. Then 2, 31.9, which is just past 30. 3, 47.85. So 47.85 is just before you get to the 50. And then 4 is at 63.80, which is just after the 60. Boom. So there's my graph. Notice how these are individual points here. They're not connected, and that's what a discrete graph will look like. All right, let's go ahead and have you pause the video and do your on your own. All right, your domain, after you did this on your own, should be 0, 1, 2, 3, 4, and 5. Your range would be 50, 41, 32, 23, 14, and 5. But what we should do is actually rewrite these in order from least to greatest, because that's what we should have. So I know that's the numbers when I plugged in 0, that's what I got. But I'm actually going to put them in order. So 5, 41, 32. Actually, I don't know why I'm putting the domain. The range. It didn't ask for the range. Oh, I'm just going to erase that. All right, instead I'm going to make my t-chart for the graphing. So here's my t-chart. This will be easier. X, Y. What you should have had was your number 0, 1, 2, 3, 4, 5. When you plugged in 0, you got 50. Then you got 41, 32, 23, 14, and then 5. To graph this, hopefully you scaled your graph. And to scale this, I'm going to count by 5s. I think that's pretty easy. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So I have my first point is 0, 50, which is up here. And then 141, which is about here. And then 232, which is about here. And then 323, which is about here. 414, which is about here, and then 55, which is here. And I guess I could write down my scale at the bottom since it's different. And there's my discrete graph for this next one. Next, let's look at example 5. A cereal bar contains 130 calories. The number of C calories consumed is a function of the number B of bars eaten. All right, so does this situation represent a linear function? Explain. And I'm going to say yes, because you have a constant rate of change. And I can see that because when I write this, I can write down that 130 calories times every bar equals the number of total calories that I'm eating. So this does even look like, from the last lesson, a linear function because of where my variables lie. Find the domain. So the domain here is, think about a bar. Let me quickly show you. I'm going to run over here and grab my own bar. All right. So here's my bar. It's a fudge dipped chocolate chip bar. So I'm going to eat this really quick. But notice I'm eating this now. This bar has, it says for one bar is 160 calories. So I ate a little less than a half of that bar. Now notice, sorry, I'm chewing right now, that I just ingested some calories. But did I ingest all of them? No. Could I eat more than one bar? Yeah. Could I eat 1.5? Yeah. Could I eat like one bite, which might be like a quarter of a bar? Yeah. So I can have partial bars or partial inputs. So this is going to be a continuous graph. I spelled continuous. Oh, I did spell it right. Good. Continuous because you can have, I guess you can say, partial inputs. Meaning bars. You can eat a part of a bar. You don't have to have whole bars. So the domain here, so those are my inputs. I can have as few as 0 bars, right? Or more. So there's no limit how many I can eat until I get sick. So I can actually just say the number of bars has to be greater than or equal to 0. And I put that on there because I can't have negative bars. But there's no stopping, like I can keep eating. Oh, that was really good. You know, it goes really good with this coffee right here. Sorry, I know this is a math video and I'm eating. Sorry. So now it says, graph the function using its domain. Oh boy. So, what we can do is use our graphing calculator, go to our y equals, type in this value, which is 130 times x. We're going to use x instead of b, and then press the table. We have a table of values here. So that table of values, x and y, is 0 bars was 0 calories, 1 bar was 130 calories, 2 bars was 260 calories, 3 bars was, what was it? 3 bars was 390 calories. Now to graph this, I'm going to just plot these points, but I'm going to make it super easy on myself. I'm going to count by hundreds here. 100, 200, 300, 400, 500. I have a closed circle. At 0, I have 0. At 1, I have like 130, which is like here. At 2, I'm at 260, which is a little more than halfway. And at 3, I have 390, which is almost 400. So what I do is, even though I have those points, since I can eat a partial bar here and have partial calories, I'm actually going to connect these with a handy-dandy ruler. And this keeps going on, both an arrow, meaning it goes on forever. And really what I should do, so I'm going to erase this, is I should use a ruler here. And my board is a little different than you using a ruler. But go through those points and connect it the whole length of the graph, not just a partial graph, and with an arrow on the end. All right, there we go. There's that one. And now we're going to go, you can do the 2 on your own, and you can ask me later how those were. Actually, let's just skip to the on your own number 10 really quick. The 20-gallon bathtub is draining at a rate of 2.5 gallons per minute. Draining means losing 2.5. So you start at 20 gallons, you're subtracting 2.5 gallons times every minute, and that's going to give you the number of gallons that are left. So if you look at this, this does represent a linear function, and that's because of the way your variable is. There's a constant rate of change. But think about the domain and range in this situation. My domain, that's the input. Input's the number of minutes. So my domain, I'm going to actually do domain and range here. My domain is I can have 0 minutes, but then when do I run out? Oh, I need to know how many minutes, and the time has to stop when I run out of water. So I'm going to go to my calculator here and graph this. I'm going to go to 20 minus 2.5x. I'm going to go to my table here, And notice at 0, when there's 0 gallons left, is at 8 minutes. So that's less than equal to 8. There we go. Actually, I'm not going to do the range because it didn't ask us to. I don't want to keep on wanting to do that. To graph this, I'm going to use my calculator here and plot these points 0, 20, and then all the way down to 8. Now, this is a discrete graph, continuous, because you can have a partial amount of time. So you can look at how much water is left in the tub after 1 minute and 37.5 seconds, which is different than 1 minute and 37.75 seconds. I mean, it's different. So to graph this, I'm going to, there it is. I'd probably scale this using probably like 2s. It's like 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So at 0 minutes, I still have 20 gallons left in my tub. And then 1, 2, 3, 4, 5, 6, 7, 8. At 8 minutes, I have 0 gallons left. And then maybe halfway through, which is 10 minutes, which is not halfway through, sorry. So between these two, because it's a linear function, I can actually connect these two dots together. But notice there's no arrows because I can't have less than 0 minutes, and I can't go more than 8 minutes because there's no water left. All right, let's go to quickly example number 6 here. Real life situations that fit these. So this is a discrete domain here. Discrete domain because there's individual points. So there's my explanation. And notice, since I'm going down, what in real life could be this? Maybe it's something like I can say I have $6. I'm just trying to come up with something. And each ticket costs $2. Okay, so that could be my situation here, because you can't buy individual tickets, and then I can only buy so many. Example B, this is a continuous function because the 2 points are connected, and maybe in this is I have 6 gallons of gas, and my lawnmower uses 1 gallon every hour. Also, if I can spell every doesn't even like, there we go, every hour. Because I can have 15 minutes of using my lawnmower, and that means it used up 15 minutes worth of gas, so that would be a continuous function. All right, that's the rest of the notes. Yeah, those were long, but hopefully not too confusing. So best of luck with this lesson, and if you have any questions, let me know. All right, have a good one.